Welcome to today's paper reading. Today's paper is titled, Schrodinger's Memory, Large Language Models. This paper was published on the AR14 preprint by Wang and Qing Li from the Department of Computing at the Hong Kong Polytechnic University. The abstract discusses the concept of memory in large language models, LLMs. It acknowledges that LLMs do exhibit memory, but the underlying mechanism is not well understood. The authors apply the Universal Approximation Theorem, UAT, to explain this memory mechanism. They also conduct experiments to verify the memory capabilities of various LLMs, proposing a new method to assess these abilities, which they liken to Schrödinger's memory, only observable when queried. Finally, the abstract compares the memory capabilities of the human brain and LLMs, highlighting both the similarities and differences in their operational mechanisms. Language models are simulations of human intelligence, particularly through the transformer architecture, which has significant impacts on daily life in areas such as machine translation, text summarization, and sentiment analysis. Despite their impressive performance, research on their memory mechanisms remains limited. Memory is crucial for humans, enabling tasks like smooth dialogue, but its role in language models is not fully understood. Current research focuses on expanding context length and integrating external memory. This paper addresses these gaps by explaining memory abilities through UAT theory, proposing a new method for memory ability assessment, and comparing LLM memory with human memory. The Universal Approximation Theorem, UAT, serves as the foundational theory for deep learning. Initially proposed by Sabenko in 2007, it states that a neural network with a single hidden layer can approximate any continuous function on a closed interval. Hornick et al. Extended this to show that multi-layer feed-forward networks can approximate arbitrary Borel measurable functions. For LLMs, the UAT form and transformer architecture allows for dynamic function fitting based on input, differing from the static nature of traditional UAT. This dynamic capability is what gives LLMs their powerful memory, enabling them to adaptively fit functions according to the input data. Figure 1 illustrates the fundamental building block within transformer-based large language models, LLMs. The block consists of a multi-head attention mechanism, which allows the model to focus on different parts of the input sequence simultaneously. This is followed by a series of multi-layer perceptron, MLP, and feed-forward network, FN, components that process the data further. The dynamic fitting capability of these models, as explained by the Universal Approximation Theorem, UAT, enables them to adaptively adjust their parameters based on the input, thereby exhibiting memory-like behavior. This architecture is crucial for the model's ability to handle complex language tasks and generate coherent responses. In this section, we explore the memory capabilities of large language models, LLMs. First, we define memory as a process triggered by input, resulting in an output that may be accurate, incorrect, or forgotten. This definition is crucial for understanding how LLMs recall information. Next, we discuss the memory mechanism of LLMs, which involves the Universal Approximation Theorem, UAT, and the dynamic adjustment of outputs based on inputs. We validate this through experiments on poetry datasets, showing that LLMs can memorize vast amounts of text. Finally, we examine the impact of output length on memory accuracy. Our experiments on the CN Poems dataset reveal that longer texts are more challenging for LLMs to remember, with accuracy decreasing as text length increases. Table 1 presents the memory capabilities of various LLMs on Chinese, CN, and English, YNG, poetry datasets. Key highlights include the high accuracy of Quen 2-1.5b Instruct and Bloom 1b4zh on CN Poems, achieving 96.9% and 96.6% respectively. Notably, all models demonstrated exceptional performance on YNG Poems, with accuracy rates exceeding 99%. This suggests that LLMs can effectively memorize large volumes of text, particularly in English, aligning with the defined memory capabilities. Figure 2 illustrates the successful recitation of entire poems by Quen 1.5-0.5b Chat, a language model fine-tuned separately on Chinese, CN, and English, YNG, poems. The model demonstrated its memory ability by accurately reciting poems based solely on the title and author, showcasing its capability to retain and generate content from its training datasets. Table 2 presents the memory abilities of various models on the CN Poems dataset under conditions of longer predictions. The models evaluated include Qwen 1.5-0.5b Chat, Qwen 2-0.5b Instruct, Qwen 2-1.5b Instruct, Bloom 389MZH, and Bloom 1b4ZH. The results indicate that as the text length increases, the difficulty for the models to remember the content also increases. Notably, the Bloom 1b4ZH model achieved the highest accuracy at 93.65%, while Qwen 1.5-0.5b Chat had the lowest at 44.9%. Figure 3 illustrates examples of incorrect predictions made by Qwen 1.5-0.5b Chat, a language model fine-tuned separately on Chinese, CN, and English, ENG, poems. Despite the fine-tuning, the model fails to accurately recall the entire content of the poems based on the input, demonstrating its limitations in memory retention. This figure serves to highlight the challenges in achieving perfect memory recall in large language models, even after specialized training on specific datasets. The paper discusses the memory capabilities of large language models, LLMs, emphasizing that they do possess memory, though it differs from traditional database storage. LLM memory refers to the dynamic approximation of outputs using internal weights and inputs. From a functional perspective, LLMs and human memory are not fundamentally different, both dynamically approximate results based on inputs. For instance, LLMs can recite entire poems based on titles and authors, similar to how humans recall specific poems when prompted. Additionally, the paper highlights that LLMs exhibit reasoning capabilities and creativity, as seen in their ability to generate outputs that align with linguistic conventions, even if not entirely accurate. This suggests that both LLMs and the human brain function as dynamic models that fit outputs based on inputs. In this paper, the authors demonstrate that large language models, LLMs, possess memory capabilities, which are enabled by their transformer-based architecture. This architecture functions as a dynamic fitting UAT model, allowing LLMs to recall entire content based on minimal input information. The authors refer to this memory as Schrödinger's memory because it can only be confirmed when triggered by input. Extensive experiments validated that the memory mechanism of LLMs aligns with this theory. Additionally, the authors compared LLMs with the human brain and found that their working mechanisms are similar, as both dynamically fit outputs based on inputs. Thank you for watching.